Hello, we are in section 2 or checkpoint 2.27. They want us to express the vector v, which is 5 comma negative 1 in component form, as the sum of orthogonal vectors such that one of the vectors has the same direction as u. Let's first generically draw the vector v and the vector u. And let's draw it with the same tail so that we can kind of see what's happening. And the idea here is we want to express the vector v. Let me redraw it here. And as a sum of two vectors. And the first one is going to be a vector that is going to be going in the same direction as u. And the best way to find that same vector going in the direction as u that's going to be matching up with v would be to take its projection. So do a projection drop down to u, and then you're going to get this new vector. Now let's call this new vector a. And that's going to be a job for the projection. And then we need to add something else to a to get to v. And so the thing that we're going to add is essentially this vector over here. So that when we add that vector, we're going to get to the vector addition of a and this new vector. Let's call this new vector b. So that when we add them, we're going to get v. And so this is what we want. We want a plus b to be equal to the vector v that we were given. Okay. And we also would note that these two vectors here would be perpendicular to each other, because we can draw that vector b over here and see that they're perpendicular. And so those are the two pieces of vectors that we're going to need. All right, let's write v down. What's v equal to? V is equal to 5 comma negative 1. So that's our main vector that we're working with. We also will need u. U is equal to 4 comma 2. And then let's focus on the projection. There's a formula for the projection. A is actually going to be the projection of v onto u. And the idea behind the projection, without kind of re-deriving it, the idea behind projection is that we're going to measure this angle theta, and we're going to project v onto w. And when we do that projection drop, you see that the side length over here is going to be the adjacent side to the angle, so that's going to have something to do with the cosine. And then we are going to be dealing with the length of v at some point, and the length of u, which is the dot product that we're looking for. In any case, the formula turns out to be, well, there's two parts to this formula. One is just the scalar length of this, and the scalar length of this is essentially u dotted with v divided by the magnitude of u. And so you can take a look at the book or see some videos about how that's derived. That's the scalar length. Now, we're going to multiply this. We want this to be going in the direction of u, and we want to scale it exactly to this length. And so to do that, we would need to multiply this with the unit vector u. And so u itself is not a unit vector. It's not necessarily, but in this case it's definitely not a unit vector, because components are 4 and 2. So by making it into a unit vector and scaling it by this value, you're going to get this green vector a that we're looking for. This can be just rewritten formula-wise as the dot product of u and v divided by the magnitude of u squared, and then multiply that by the vector u itself. Okay, we have the vectors v and u, so let's go ahead and do the computation. U dot v is going to be 5 times 4 plus 2 times negative 1 divided by the magnitude of u and squaring it, so it's really just u dotted with itself. That's going to be 16 plus 4, and this is going to be 18. Oops, we need to multiply by the vector u, so let's not forget about that multiplication. Multiply that by the vector u, which is 4, 2. And that will leave us with 20 minus 2 is 18. And this is going to be 20, and the 4, and the 2. Suppose we can simplify this just a little bit. Let's divide out 9 and 10. Oh, but the 10 is also has a factor of 2 that we can take out from here, so that will be 2 and 1 after we take out 10, and then another 2, so that's just 5. Okay, should double check that to make sure that that works out, but this is the vector A that we're looking for. Now to find B is really just the difference between V and A. We know what V is, we know what A is, we just found A, so we should be able to figure that out. So B should equal to V minus A. Well, yeah, we can figure that out here as well. So V was 5 comma negative 1, and A we just found to be 9/5 times 2 comma 1. I suppose we could have worked that out in there, but we can do it now. Let's have 5 comma negative 1 minus, that's 18/5 comma, and I just distributed the positive because the negative is still out here, so 18/5 and 9/5. Okay, and common denominators would be 5. This is 25. 25 minus 18 is, I think it's 7. And negative 1 minus, so we're essentially adding them with the negative sign. And so that's 5 plus 9 is 14. And same denominator, 5. Okay, so this is your B vector. So we should check that if we add A and B that we're going to get V, because that's our condition. But we kind of did that work already, because that's how we found B. And then the other thing to do is to double check. We can take the dot product. Actually, before we take the dot product, let's take a look at this. This looks like it has a factor of 7/5 in it, so let's take a 7/5 out just to try to make things easier for us. And we take 7/5 out of 7/5 is 1. We take 7/5 out of negative 14/5, we get negative 2. Distribute that to make sure that that's done correctly, but I think it's right. And finally, let's check. So we know that this should be true. Now let's just check to make sure that this actually does work out, that A dotted with B should equal to 0. And A is 9/5, 2 comma 1. B is 7/5, 1 comma negative 2. So we can take the constants out. This one of the properties for the dot product. If you have constants, we can take them out. So let's multiply 9 and 7 is 63. 5 and 5 is 25. And then now let's take the dot product of these two vectors. So we have 2 times 1 minus 1 times negative 2. And so that's going to give us a 0, and that's exactly what we're looking for. All right, so projection, you get your projection vector, you subtract to get the vector that's perpendicular to the projection vector that you just found, and then you're pretty much guaranteed that the sum is equal to the original vector v. And then if you want, you can double check by taking the dot product, and you're going to get 0 because they're perpendicular. Okay, I hope that helps.